made the mistake of closing my computer. Okay, hi. I'm going to be talking about WebSockets today. As you might already know, WebSockets are a protocol created by Google, and the problem that they solve is real-time collaboration. So you've probably used like Google Docs or Trello or like online like multiplayer games. And so like when you're like editing in Google Docs, if you're sitting next to your friend and you have the same doc open in 2 different computers, you expect that if you make a change to on your computer, like make something bold, fix a typo, whatever, by the time you turn to your friend and say, you know, I fixed it, by the time you even look at their screen, it should be already like fixed on their screen. So it needs to be real time, so that we want like very low latency between you making a change and it showing up on your friend's computer. We also need two-way push, because when you make a change on your computer, your browser needs to push the change to the server, because your browser is the one who knows there's a change. And when the server pushes something to your friend's computer, your change, the server knows that there's a change. So you need both directions to be able to send data with low latency. We also need something that's specifically for a browser to a server, because if you're going to have JavaScript be able to do something on a web page, you have to have already like implemented it in the browser, which means it needs to be standard, so it can be like the same across all browsers. And so the solution we're talking about is WebSockets. And so it's the connection between the client and the server. It goes in both directions. It uses one TCP socket, so you don't have any like extra round trips to set up the socket before you can even start sending your data. TCP sockets work in both directions, and you can send at the same time, and that takes care of that stuff. And then WebSockets have a standard. There's an RFC for them, which is the main source for my talk. So WebSockets are inside a TCP socket, as I said, and there's sort of like 3 phases. There's the opening handshake, which is HTTP. There's you exchange data, which is the WebSockets protocol, and unfortunately something is covering it, but there's the closing handshake at the bottom. And so we're going to go through these 3 phases in order. And so the HTTP handshake is just you send an HTTP GET request, and then the server sends back an HTTP response with the status code 101 switching protocols. So this is already built into HTTP. This came well before WebSockets. WebSockets is just the first mainstream thing to really use it. And so these are completely valid HTTP, this request and response. After that, this TCP socket that you've been exchanging HTTP in turns into a WebSocket. So you keep using the same TCP socket the entire time. It's just now we've agreed to use it for something other than HTTP. And in this handshake, this like one request, one response, we have to get a bunch of stuff done. We need to agree that we're doing WebSockets. We need to agree on what version. We need to agree on 0 or 1 subprotocols, which is just a way of what we're going to put in our messages. And we can agree on 0 or more extensions. So subprotocols and extensions are like slightly different, but they're both just ways of building on top of the basic WebSockets protocol, and so you don't have to use either of them if you don't want to. So this is the GET request. So it's always going to be a GET. That's just how you start it. The top part there is just part of doing an upgrade request. So we want to upgrade to WebSockets, and we want to upgrade our connection. And that's all that's saying there. And then the next header we haven't talked about yet. We're going to talk about that in a minute. That's the WebSocket key. And then the next 3 are the ones we already mentioned. So we're going to ask about subprotocols, versions, and extensions. And these are things we need to agree with the server on. The server's headers look pretty similar. It has those upgrade connection things that it says back. And then it has an accept, which is the match to that key from the client. And that's both of those are base 64 numbers. Base 64 encoded numbers. And then we have the protocol and the extensions. So in this case, the server is agreeing, it picked one protocol and picked one extension. It does not have a version header because the client only sends one, so if the server agrees with it, then it does 101 switching protocols. If it doesn't agree, it'll respond differently. So first we're going to talk about that key accept thing, because that's like the weirdest looking one. And so the client sends a key, the server sends an accept header. And so the client is picking a random number. So it picks a random number, and then it sends it to the server base64 encoded. The server takes that string that it gave it, and it does some deterministic magic, and it ends up with another base64 encoded thing, and it sends that back. And the important part here is that the client picked a random number, so it's different on each request. The server did something with it that the client can then check, and it's just this like random thing the server does that's intrinsic to WebSockets. So unless a WebSocket server gets the request, you're not going to get an appropriate response. And in particular, you append this special constant from the RFC to the base64 encoded string that the client sends, and then you take a SHA-1 hash of that, and you get some bytes, and then you base64 encode those bytes. And so the top line is what the client sent in its key header, and the bottom line is what the server sends back in its accept header. And you're probably wondering why, because like we're passing a number back and forth. This doesn't help our negotiations at all. And so this is because the internet is full of caches. It's basically made of like tubes and caches. Because every time somebody wants to make your internet faster, they stick a cache in there and go, okay, if you see a request, remember what the response was, and then just if you get that request again, just give the same response. So you can often, when you send an HTTP request out into the internet, you don't actually reach the server you thought you were going to reach. It's just some cache is in the way and gives you a remembered answer. And usually this is fine. But if you think about like when we're opening a WebSocket, except for that WebSocket key, the rest of it is always going to be the same from your JavaScript web page. You're going to pick the same options. You're going to go to the same server and the same URL. So it's all going to look exactly the same. And some cache in the middle is going to go, hey, this is HTTP. I understand this. Let me just watch and see what the server responds. And then next time you try to open a WebSocket to your server, it just stops working. Because some cache went, oh, here's the response. Let me close the TCP socket. And your computer, your JavaScript clients are going to be very sad because they agreed with the server to do WebSockets, and then the server closed the TCP connection. So instead, we have this randomized number in the client that the server has to then deterministically make into a different number. And that way, so the caches won't cache it because there's a random number in it. And even if they were like, well, that header probably doesn't mean anything, the client can still tell because the server's number will not match. So it'll understand like something is happening. I did not get to talk to my WebSocket server. And so once we've assured ourselves that we are speaking WebSockets and we are actually talking to a server that understands WebSockets and not some cache, we can get onto our negotiations. So if the client sends version 13, which it did in our example, the server doesn't include a version header. The server is just like, cool, like you picked exactly one, I'm okay with that version. If the client picks a version that doesn't exist, like 25, the server sends in HTTP 400 instead of a 101. It sends 400, and it'll include a version header that's a list. So it'll list in order of preference. So in this case, it says 1387. And so the client could start over with a new HTTP request of the same format originally, but picking one of the versions the server is okay with. And if it doesn't like any of those versions, then they just can't talk. And so version 13 is like the version of WebSockets. There's a few previous versions that are draft versions, but only official release version is 13. And now we can also negotiate subprotocols. This goes a little bit different. So the client gives a list, but we only want to end up with one. So the client lists the subprotocols it likes in order from its favorite to its least favorite, and then the server picks the first one that it supports. Or the server can pick any of them, but it's supposed to pick the client's favorite one that it supports. So in this case, it picks chat. We'll talk a little bit more about subprotocols later. You can have exactly one, and they change how your data and header, your application data is interpreted by a little bit. But there's a bunch of them registered, but there's not a general one that would be interesting to present. We will be talking about a specific extension though. And so when you negotiate extensions, it's very similar to subprotocol negotiation. The client lists some stuff that it would be happy to use, and then the server picks what it wants to use. Unlike subprotocols, you can use multiple extensions, and it's the responsibility of the client and server to pick ones that work well together. The client can pick multiple things that conflict, and then the server has to pick the subset of those that it understands and that won't conflict, and then sends them back. So the client is offering some things, and the server is choosing what to actually do. So in this case, this is from the RFC. They made up some extensions to use here. So there's mux that has like a couple of settings, max channel and flow control. So mux is the name of the extension, and then there's a semicolon, the name of a property of it, and then it equals 4, and then a semicolon and the name of this other property. And so this means that you're configuring this algorithm with specific settings, like this setting for max channel, and like this turning this feature on flow control. And then comma, it offers a second option for an extension, which is deflate stream. And so in this case, the server picks deflate stream. So it picked one of the two extensions. It could have picked both. These client also could have offered mux multiple times with different options if it wanted to say, I like this set of options, or I could also do this set of options. The server, if it understood what mux was, it would know whether it had the option to just turn off flow control by just not including it in its response. They could also pick two, in this case, it could also pick two extensions by like picking both of them, and depending on the extension itself, it controls like whether it's allowed to offer, say, fewer max channels. It can also just not take any of them. It's like if your server is like, I don't understand what extensions are, I'm just going to ignore it, then you just don't return that header. You don't have to use extensions. The client is just offering them. So this is this is like these are basically the same setup between the subprotocol and the extension negotiation. The main difference is that extensions have more properties and you can use more of them. So ordering is important on both sides in extensions. The client lists them from favorite to least favorite, and then the server lists them in the order that it will apply them. So if it picks 2, it will apply the first transformation to your packet and then the second one. And so the client will have to apply them in reverse order. So like if you were like encoding it multiple ways, you'd have to the server wraps them up in order where the first one is the innermost layer, and then the client has to unwrap them in reverse order. So we've done our handshake. For the rest of this exchanging data thing, which is the middle part of the connection, the main, hopefully the longest part of your connection, we're going to be assuming there's no subprotocols, no extensions. We're just using version 13 of Websockets. And so Websockets is message-based, which you'd know if you use the JavaScript interface, which is you can receive a message, you can send a message. And then there's some underlying stuff that we're going to talk about here that you wouldn't see if you'd use the JavaScript interface. So the server can send messages, the client can send messages, and as you can see in this diagram, it's important to remember that the client's messages are always masked, and the server's messages are never masked. This is not, I'm going to explain what masking is and why we do it in a minute, but when we look at the structure of how these go on the wire, there's going to be this stuff about masking, and you should just know that this is just client sends masked messages, server doesn't. And so we have a couple different kinds of messages. So you can there's data messages and control messages. Data messages are what the application is sending. So the application, the JavaScript or your server application sends data to each other. So it sends text or binary messages. Text is UTF-8, binary is arbitrary binary, whatever you want. And so the application is responsible for parsing the binary into whatever format it understands. The control messages are for the lower level connection, so the JavaScript won't see these. And so you can send pings and pongs and closes. So if the server sends a ping to the client will respond with a pong. So those are just a pair of messages, basically to say, are you still there? And then there's a close message, which is part of our closing handshake, which we'll talk about at the end. Messages, so I sort of simplified these messages. So these text and binary messages, the data messages, are actually aren't sent as one block. They're actually sent as a series of frames. So we have a text message, hello world. We could send it in one frame, in which case we'd mark the frame, this is a text frame, and it's the only frame in this message, so we send it. Or we could send it as 2 frames, so we just split the text into 2. We do need to split it along character boundaries, but otherwise you can split it however you want. We're just going to append it on the other side, so this will give you the same output. And you could do it with even more. You could split it into 4 frames. It doesn't matter how many frames you want to split it in. The other side will concatenate them together, and the JavaScript won't be able to tell the difference. So that's an important thing to remember about frames. They're an implementation detail. They are not important to your JavaScript applications. That only sees messages. So you remember why are we making this more complicated? We had messages. These frames don't seem that much different. And so there's a couple of options when you're designing like a protocol to send stuff between two endpoints, which there's many options already. And so a lot of the sort of more basic ones like TCP are streaming protocols. And this is like kind of complicated to implement on each side. Like often you want to end up with a message API, which is like what most modern APIs are. And that means that your code, you have to do all this parsing and buffering to get to your messages. So we're going to do messages because we can still do streaming APIs if we want to, even if our underlying protocol involves messages. And so once we've decided to do messages, we fragment them because that means we can do streaming APIs. So like if your application is like streaming this like long blob of data, maybe like there's like some kind of real-time data that you're reading from the real world, and you're just streaming it down a WebSocket as one message. And so the underlying stuff doesn't know when you're going to finish sending it data, or like how many like gigabytes of data you're going to save from your webcam before you're done with your WebSocket message. And so instead, it needs to be able to send one frame at a time, so that it can make a whole frame and doesn't have to hold on to your data. Because our headers so WebSockets uses messages and headers, and so the headers have to go at the front, and the headers include the length, and so you can't send your message until you have the length of the entire payload for that fragment. And headers are really nice because they're easy to parse. They're generally just easy to implement because you can parse all your nicely formatted headers, and then you have a blob of data. And you'll be able to tell when your blob of data ends before the next fragment starts. The other option, other than headers, is basically to use delimiters, but that gets pretty messy once you have arbitrary binary data that you then have to like escape some of it and unescape it, because there's no like out-of-band stuff because it's all binary. You also can't insert control messages in the middle of like a delimited thing. It'd be much messier, even messier than like having delimiters at all. So WebSockets uses messages, not streams, and it uses headers, not delimiters, to separate those messages into fragments and to separate the messages from each other. So now we're actually going to look at a frame. I told you about this sort of upfront stuff about sort of how messages and frames work, and now this is a diagram from the RFC. And so it's 32 bits across, and you can see them numbered at the top, starting from 0, ending at 31. And so each column is 1 bit. So we're going to work from left to right through all of these bits. So the first one is the fin bit. And so this tells you whether this was the last frame in the message. So if I have 1 frame in my message, I'll just put a 1 in the fin bit because I'm the last one. If I have 2 frames in my message, I'll put 0 on the first one and 1 on the second one, because the first one is not the last one. And then if I have more than that, I can do a bunch of zeros and then a 1. And I'm showing in the middle there, this is a 4-part message, but there's a ping that happened in the middle of it. And so that ping is just a control message that's all by itself. And this is one of the reasons you can stick control messages in the middle, is because of the opcode change, which actually we haven't gotten to yet, so the slide is out of order. But so you start with a 1. If you are 1, the 1 is always the last one. So even if you only have 1, you just set the fin bit to 1. The next section is a set of 3 reserved bits, which always have to be 0. They're pretty boring because you don't do anything with them. But it's important that they're always set to 0, and you end the WebSockets connection if any of them are not 0 and you weren't expecting it, because otherwise they won't stay reserved. And we'll talk about these. The reserved bit number 1 is used in the extension we're going to talk about at the end. So the next section is we have 4 bits of opcode. And so this is how we tell the different kinds of messages apart. So this is that thing I was talking about, text, binary, ping, pong, close. These are all the different opcodes. And so we'll talk about what values those specifically take on, but this is what the opcode encodes. The next part is the mask. So there's a 1-bit flag for whether this message is masked or not, or whether this fragment in particular is masked or not. And so if it's set to 1, then there's a masking key later in the thing, before the data. And so masking is just, so this is what the client is doing on top. The client is going, okay, I have my original data. I'm going to XOR it with this masking key, which is a secure random number. So it's the client is responsible for picking a random number that the JavaScript will not be able to guess. So they have to make it unpredictable. So it will have the masking key and the original data, XOR them, and stick them both in the packet. And so then the server receives the frame, it takes the masked data that's in there, it XORs it with the masking key, and then it gets the original data back. And so all you have to do is understand WebSockets, and you'll be able to unmask the data from the client. You'll even be able to tell whether it's masked and what key they used. Like, everything is just in there, which might make you wonder why we mask data, and only from the client. So this is another security thing. It's not secrets. You're not trying to keep the data secret. That's why you would connect over, the WebSockets has an HTTPS equivalent where it has all the TLS stuff. But so this is for those caches again. So there's a cache poisoning attack. If you trick someone into going to your website, and so they have this like evil client running on the machine, and they talk to your evil server. And so you're trying to trick the caches in the middle to believe that the version of a file you give them is maybe like jQuery as served by Google. And so that everyone will now get this evil jQuery instead of the good one. And so you could do this with WebSockets if the client didn't have to mask its data. So if you're going to try to do this, you would set up a WebSocket to a server you control. The WebSocket should send a payload to the server that looks like an HTTP request. And so if this was not masked, some cache in the middle could go, oh, hey, that looks like HTTP. I don't understand these bits at the front that are like the WebSockets frame, but that's HTTP, and I'm supposed to grab HTTP requests. And then it'll pass it on through to the server, and the server, because you can control it, can send back whatever evil payload you want to be the response. And the cache will go, oh, I see an HTTP response to go with my HTTP request. I'm happy, I'll save that pair. We'll throw away those extra bytes at the front. Who knows what that was? And then the next time somebody sends an actual request that looked like the one it cached, it will serve up your evil jQuery instead of the real one. And so, while caches are caches are easily misled if you can send sort of plain text HTTP in front of them, and it's especially dangerous for cache poisoning because if you get some one person behind a cache to open your evil website, then everyone's cache will be poisoned. Which is why the client has to mask, because you can get, if you get somebody to open a web page, they have a client that talks to your server. But the server is not as helpful for the server to be able to the server is already sending whatever it wants. And it cannot manufacture both sides of a request response. So the next thing we're going to talk about is the payload length, which is all of this stuff. It's like half of the diagram. It's actually pretty cool. So the length, if your length is in bytes. So if the length of your payload is 125 bytes or less, then you can stick that length in the 7 bits after mask. So mask plus the length is 1 byte. And so that up to 125, you just stick it as binary in there. So that's that top row where it's a 7-bit length. But that might not be long enough. Maybe you prefer to have your message all in one frame, even if your payload is longer than that. So instead, you could use 16 bits, in which case you'll put 126 in your 7 bits, and then, the next 16 bits will be used for your length, which in this case, you can put 126 again. And if you're making your message one byte longer, then your length will be 127, which you'll still put 126 in the first 7 bits, and then 127 in the next 16. And then if you want to make your length really long, you can put 127 in those first 7 bits, and then you have a whole 64 bits to put your length. So it can be you can have a lot of bytes in one frame if you wanted to. I don't know why you would do that exactly, although I'm sure there's maybe something with streaming video or something, or just somewhere in the future, 16-bit lengths will not be enough for one frame. But see, it's kind of cool because you have this switch off of 125, and then so 126 and 127, the ones that we use to make the length longer, are also the highest 2 values that you could represent with 7 bits. So now we're going to go back to those opcodes. So opcode is 4 bits, which means we have 0 to 15. So not that many options, and unlike length, is not expandable. So these are the only 16 options we have for the entire future of WebSockets. And so we've used so the bottom half, the low half is 1 through 7 are used for data frames. So there's text and binary, which are already defined, and then the rest of them are reserved for future use. So you're not supposed to use them. You should fail the connection if somebody uses them. And control frames are the high half, so we have close, ping, and pong, and then the rest are reserved. So we've only used 5 so far, so we have lots of space left in our opcode. 0, which I hadn't mentioned yet, is used for fragmenting. So if, sorry, my slides are not in the order they should be. So if I go back to here, which shows the opcodes conveniently, the top one is text, which we've seen. The second one is binary, which is the other data one. And then the one after that says continued. So the first frame in a message will have the opcode for what kind of data is going to be in there. And then the rest of the frames will all have 0 because they're just, you don't have to say it again. We already said what type the message was, and you can't change it. So you have binary and then all zeros for the rest of them. And so this also means that you can't interleave data messages. So like I do text and then the rest of the fragments, and I can interrupt it with a control message because control messages are always one frame. So it's fine to put ping in there. It will always have the fin bit set. Totally cool. Or pong if you wanted to. So if you were in the middle of streaming a long series of frames for a really big message, you can stick a ping or pong in there. And if you wanted to, you could even like, you could you have some data, you send your frame, you send your ping, you're good. You can break up messages freely as long as it's still frames of part of the same message. Okay, so now that I explained, so that I've told you so far all sort of the aspects of the WebSockets protocol, and so I'm going to tell you about an extension. I'm actually pretty excited. The last time I gave this talk, there wasn't any IANA registered extensions yet, but now there is one. And so you can register register WebSockets extensions and error codes and sub-protocols with IANA. And so if you search WebSockets IANA, you'll see a whole list of like all of the officially registered ones. And the only registered extension is per message deflate, which is defined in RFC 7692. And so the point is basically, so you remember we had the HTTP handshake, and when you do HTTP, you can like set all these compression stuff for like how you're going to send your files, but you lose all of that when you do WebSockets because those weren't WebSockets headers. We ignored them, so now we're just sending uncompressed data in both directions. So instead, you can set up this extension which lets you compress message payloads on a per message basis. So each message that you send can be either compressed or uncompressed. And so you'll negotiate it up front. Per message deflate means that you're going to use the deflate algorithm, and there's some specific settings you can set up, but they're not super interesting. It's just like, I showed you how you negotiate extensions, and there's like specific ones there, but it's just about like how this specific algorithm and making sure that we use the algorithm in the same way on both sides of the connection. So the client will offer some settings, and the server will pick some settings, and then they'll do it. So the way the extension actually works is it uses reserve bit 1 in order to say whether a message is compressed or not. So if we set the reserve on the top left, we've set reserve bit 1 to 1, and so this gobbledygook is like some compressed text. And then on the other side, we could have the equivalent frame with reserve bit 0 set to 0, or reserve bit 1 set to 0, and then we'll have just our text. So they're equivalent. You can also break them up into separate frames. And so the interesting thing here is reserve bit 1 is 1 on the first frame of a compressed message, but it's 0 on the rest because, well, you already know that this is compressed because you saw the first one. So it becomes 0, kind of like the opcode becomes 0. So you just know that, and so when the client or the server gets this compressed message, it concatenates the compressed data and then uncompresses it. So you're sending frames of compressed data. And so it's like relatively simple, but it sort of adds back in this feature that we sort of lost when we switched from HTTP to WebSockets for sending data. And so then we have the closing handshake, which was the end of our WebSockets connection, and is separate from like closing the TCP socket. And of course, you could close the TCP socket. You could close it at any time, and our WebSocket would be over. But instead, we can close it nicely by sending a close message and then the other side will send a closed message back, and then the WebSocket is closed. The point of sending a closed message is so that the other side can tell that you're done sending data, because you're not allowed to send any. It's illegal to send any packets, any more frames after your closed frame. So once you send closed, they're like, okay, I got all the data you were sending, rather than like leaving them wondering whether they got like a valid like piece of data, like whether they got the whole file you were sending them. And so the closed packets look pretty much like a lot of the other control packets. So we're going to have our upcode for close, and then the close has a specific body format for its payload. The first 2 bytes are a machine-readable error code, and then the rest of it is a human-readable optional message string. And the body of the close is entirely optional, but it's nice to give them some feedback on why you closed the connection. For example, if you were going to send a protocol error, you could tell them what went wrong with the protocol, such as using a reserved opcode. And so 2-byte status message, so a status code that's machine readable and defined in the RFC, and then a human readable message. So these are some examples from the RFC of close statuses they already came up with. So 1,000, normal close, 1,002, protocol error, 1,009, message too big. And so these are they also picked out ranges of what you use for what. So 0 to 999 are not used. 1,000 to 3,000 are defined by the like main WebSockets RFC, and then they're reserved for future RFCs. And then you have some registerable ones, and then some ones that are not registerable. So it's like, okay, we have all these bytes, we have thousands of error codes. Let's divide them up, and so we'll have plenty. And so we've talked about WebSockets from the handshake through the actual like data protocol onto closing it, and we also talked about one registered extension. And so this protocol is pretty cool. Like there's all of these like edge cases and things you wouldn't necessarily expect if you just like were like, well, we need to send some data between like a browser and a server, and we just want to keep a TCP connection open and send some data over it. So one thing that's nice is from the handshake, you agree in like pretty great detail what exactly you're going to be doing. So we're going to upgrade to WebSockets, a particular version of WebSockets, possibly a particular subprotocol, and particular extensions. So you have a lot of parameters that you can control over your WebSocket, which makes it very extensible, both for like future-proofing, like for each new kind of compression or whatever, we can add a new extension that follows the same format of the existing one. And like we can add like new subprotocols of some new format, like whether it's JSON or XML becomes popular, you could add a subprotocol that just says I'm going to be communicating only in JSON. And so like you can agree in great detail over like the parameters of your WebSocket, and there's lots of like it's like very specific what exactly you're agreeing to speak. You also leave room for growth. So like there's those reserved bits. There's this huge length field. There's extensions, which themselves are like an enormous like room for growth thing, because you can completely change your protocol or change it to large degrees while keeping this like pretty like stable base. And so that's often an important thing to remember, like when you're doing your own protocols, like even between like your company's client and your company's server, it can be really helpful to include a version, even if it's just your like little made up JSON protocol, because someday you might go, oh, it's really be helpful to like remove that field or add this other field. And if you include a version, it means that one side or the other both can be backwards compatible, so you don't have to worry so much when you're deploying it. Like having versions is super helpful. And leaving like if you're like doing a protocol that's low enough level to have like individual bits have specific meanings, it's helpful to leave a few extra, just in case you want to reinterpret the rest of the message. In case with the reserve bits, it's helpful to have them up front because you can change anything from the rest of the message after that fin bit. The other thing that was especially surprising to me when I was reading this the first time is all this consideration of like non-endpoints, like all those caches in the middle. Like I wouldn't have, like, it's really confusing. Why do you mask? Why do you send this key and accept? And like when I first was implementing, I was like, okay, you need a key header and accept header, and here's the algorithm. I don't understand why they're doing this, but okay, I'll implement it the way you said so that Chrome will talk to my server. But it's really interesting that they had to do all of this, like making sure it works in the real world with all of these things that are not real, don't actually understand WebSockets. And they did actually do experiments, and like the cache poisoning attack does work in the wild, which is why they included it in the RFC. But But thanks for listening. My main source is the RFC. This is the one for WebSockets. There's also the one for the extension. And the way I got excited about WebSockets was I wrote the Julia package for implementing a WebSockets server. And I'm happy to take questions.
It seems like WebSockets is really sockets, not HTTP at all, but over HTTP. And so a lot has been done to make sure that things along the way don't cache things. But there's still lots of things like proxy servers. They could be someone's trying to cache them, or it could be like a corporate proxy because you can't connect to the internet, so we put a proxy server there. Do you have any idea what it's like, are there proxy servers that support this so that, I can make regular HTTP requests? Will proxy servers let WebSockets through? What do? Are there recommendations for how to do compliance on these kinds of things? We need to track what people are doing across these connections.
I'm not aware of stuff like that because I've mostly just implemented the protocol as written. I'd imagine that one of the reasons that they have an HTTP handshake is so that they can get past stuff like that. That's like expecting HTTP. It's like, we'll let HTTP through, those TCP connections are fine. And so you do the handshake, and then you just start using the TCP connection for WebSockets instead. I expect that's part of the reasons why they do HTTP handshake at the beginning. I don't know anything about whether there's proxies that do the compliance stuff on WebSockets.
Can you pool WebSockets on the server side the way you can with normal sockets just to increase the number to scale up? Sort of pre.
So the client controls how many WebSockets are open to a server because it has to open each one. The server can do whatever it wants with the TCP sockets as long as it speaks WebSockets over them.
Okay.
You only have one TCP socket per WebSocket. There's no way to say that this WebSocket corresponds to multiple TCP sockets.
Right, but when the server side is done with one client, can it switch over to sort of be reused in some way?
Yeah. So the protocol is only about what you speak over TCP sockets. So the server can do whatever it wants as it switches between different clients.
Oh, okay.
Is this intended purely for web client to server?
So it's definitely specifically designed for browsers to servers. You could totally use it between other servers if you wanted to. It'd just be a little silly because now you're masking data from your client, even though it doesn't really matter.
Yeah.
But yeah, the protocol could totally be used as just a message-based protocol over TCP if you wanted to.
All right, thanks.
Okay, I don't see anybody else walking, so I think we're done with questions. Thank you.